in the last class we were talking about dislocations, and before we proceed, let us just have a look at what we were talking about. We said about the dislocations, the Burgers vector of a dislocation remains invariant even though dislocation line may be a curvilinear line, and the sum of the Burgers vector of dislocations which meet in a node is 0. And we also said that dislocation cannot end abruptly in the crystal. It either meets in a node inside the crystal, it can close on itself in the form of a loop, or it has to end at the extremities, the surface of the crystal. And then we also said that stored strain energy per unit length of the dislocation line is 1 by 2 mu is the shear modulus times the square of the magnitude of the Burgers vector. So that's something we talked about in the last class. And we also said that because the energy of the dislocation is proportional to the squares of its Burgers vector, the dislocations tend to have as small a Burgers vector as possible, because I also said that by their presence, dislocations in the crystal, they are increasing the free energy of the crystal. Okay, so therefore the tendency for them is to have the as small a Burgers vector as possible, and this is what we found as the smallest displacements which are possible in these crystals for a full dislocation. And we also said that opposite dislocations lying on a slip plane, they attract each other. There is an attraction between them. If the facility is provided to for them to come closer, they can annihilate each other completely. And on the other hand, if the dislocations are of the same sign, they lie on the slip plane, they are repelling each other. If they have to come together, there have to be a lot of increase in energy is there. That energy is provided by an external source. So they cannot be normally brought together, they can go away from each other. Then we saw the interaction of dislocations. A dislocation of the same sign will attract in this region and in this region, while the attraction would be of the opposite sign dislocation in that region. And this division lines, blue lines are the ones which are dividing these regions into 4 parts, and that's what we saw, because the strains below this are tensile in nature and strains above this are compressive in nature, and therefore in this volume there shall be a cancellation of the strains. Then I think in the last of the class we were talking about the interaction of dislocation with the point imperfections. If I have an interstitial impurity atom, it would like to stay here, because that's where the interstitial void is very big in volume as compared to anywhere else. And if it is a smaller substitutional atom, it would like to sit in a compressive region here, where the space is small available. However, the space available here is bigger, so bigger atom would like to sit there. So that's how these point imperfections are interacting. The purpose is, or the intention is, to reduce the stored strains in the material, and with the strain are stored the strain energy, which goes to increase the enthalpy of the crystal and thereby the free energy of the crystal. If that is to be taken care of, the interactions would be such that free energy is lowered, and therefore this bigger atom, which causes compressions all around, would like to sit in a tension side of the dislocation, so that part of the strains of this compression are cancelled by the tensions of the dislocation, or tensions in the dislocation are cancelled by the compressions around the bigger substitutional impurity atom, and so on and so forth. Well, the density of a dislocation is usually given as total length of the dislocation line in the unit volume of the crystal. Therefore, it is expressed as meter per cubic meter, which also can be written as per square meter. Unless there is a small difference between them, is a factor of 2. In this course we shall ignore that, because in the second case, what instead of measuring the length in the total crystal, we are measuring the intersection the dislocation lines are making on a given unit area, and we count those points in the given unit area. So that number per unit area, that's per square meter, is the expression for that, and that's what we use. But anyway, we will use this interchangeably, meter per cubic meter, per square meter, because even in a well annealed crystal where dislocations have, with the help of thermal energy, have gone out of the crystal as far as possible, still I am left with of the order of 10 to the power 8 to 10 to the power 10 meter length of the dislocation line in a cubic meter of the crystal. So that high A density is still there. No? Now we shall look at, after having looked at the static properties of the dislocation, shall like to look at the dynamic properties, the motion of the dislocation in the crystal. One simple motion of the dislocation in the crystal is called the slip motion or the glide motion of the dislocation line. The plane that contains the Burgers vector and the dislocation line vector, you would have noticed, is the slip plane. That is how I call the plane the slip plane. It contains both the Burgers vector and the dislocation line vector. And when the dislocation moves, it moves on its slip plane, remains on the slip plane, it is the slip motion or the glide motion. And the direction of motion of the dislocation line is perpendicular to T, irrespective of what way the B is pointing. It's a material, it goes perpendicular to T. And for the edge and mixed dislocation, it is uniquely defined. The slip plane for screw dislocation cannot be uniquely defined. Why? Why I cannot uniquely define this slip plane of the screw dislocation? It's because the Burgers vector and the dislocation line vectors are parallel. Means the same vector is one vector, and one vector can lie on infinite number of planes passing through it. Okay, so therefore it has large number of slip planes, not infinite. There are some crystallographic planes, so it has large number of slip planes. The screw dislocation slip plane is not unique for that, but we shall see the slip motion in all kinds of dislocations. Let us see this edge dislocation first. This is the edge dislocation. And dislocation is located here. From this place, if I apply a stress to these atoms which are above this slip plane is here. Above this slip plane, I apply the stress to the right, and to the atoms below I apply to the left. I can bring this atom closer to the right slightly and this one slightly to the left, so that this row of atom joins with this row of atom that forms a bond, and this dislocation or the part plane would have come here, because this bond would have broken when the bond is formed here. this bond would break, and therefore this becomes a part plane. Let me show you that how it happens when I apply the stress. This is how it happens, step by step, Then if you continue to apply the same stress, this atom will now still shift to the right, this one will try to shift to the left, and they will form the bond, while this bond will break. Let's see what happens next. Okay. Similarly, this force which you applied continues the stress, the shear stress, and see what happens. This goes on, and the dislocation gets out of the crystal. Now there is no dislocation in the crystal. It's a perfect crystal. Only thing, the shape of the crystal has changed. It has formed a step here, it has formed a step there. You might have started with a perfect crystal, and dislocation got introduced at this end, and when it made to move, it went onto the other side and caused a step. Shape of the crystal has changed, right? Let's go back and start in a faster mode. See how it is going. You can see it again. This is what is the slip motion of the edge dislocation, and it is moving on the slip plane, and the dislocation line is perpendicular to this plane of the screen, and dislocation is moving perpendicular to that, right? Let's look at the screw dislocation, the same motion. I think you can see this is the configuration which I have for the negative screw dislocation, which we saw earlier, and the dislocation line is from here going inside the crystal to the other end, and this is the Burgers vector of the dislocation line, which is opposite to the dislocation line vector depending upon which way I chosen the dislocation vector. It's a negative screw, and this is the slip plane. This is a slip plane for the dislocation line, right? Because right now it is on this plane. So we'll see what happens when it moves step by step. It goes backwards. When I am applying the stress, top part to the right, bottom part to the left. This moves on, and the dislocation moves by one step. See, it moves by another step. It moves by another step. Moves by another step. When dislocation gone to the back surface, you got a step formed like you formed the step in the edge dislocation. It's similar to that. In other words, the step which you have formed here and there, that's in terms of the Burgers vector. Irrespective of whether it is an edge dislocation or a screw dislocation, this displacement ultimately which we have got on the surface of the crystal is the Burgers vector of the dislocation line. And dislocation in this case has moved backwards. The stress applied was the same. You applied top part to the right, bottom part to the left. That's a shear stress in that fashion, right? Right. You can see this in a little faster motion now. Okay. Once more. This is the glide motion or the slip motion or the screw dislocation, right? Now let's look at the mixed dislocation line. Here is a mixed dislocation line with the edge dislocation component on this and a screw dislocation component here, which is the negative screw. This is a positive edge, and the dislocation line goes inside the crystal like this. I showed you this in a transparent picture. This is the opaque picture, but let's see how the dislocation moves step by step. Notice that this position is for the edge dislocation, that position is the screw dislocation. Carefully look, what happens when it goes by one step. Edge dislocation moves by one step to the right, screw dislocation component moves to the back by one step. That means the loop which is in, or the arc which is inside is increasing in size, right? Just see that next. It's further gone down there, so arc has become still bigger. As is still, and now the next step it will go out of the crystal. Again the step formed finally is the same as a Burgers vector dislocation line, right? So now you can try to see the same motion. This is the slip motion or the glide motion of the dislocation line, which is a mixed dislocation line, right? So all the time dislocation was moving perpendicular to itself. Say for example what on this slip plane, let us say this is the dislocation line I have. It shall move this component perpendicular to itself, this component perpendicular to itself like this. So this moves here. Next time it moves like this. So all components move perpendicular to itself, okay, all the time. So any segment you take of the dislocation line will be going perpendicular to itself all the time. That's how it is moving. That's the direction of the motion.
Can you show the previous slide again? Slide motion.
Glide motion again.
Yes,
I have to. Okay. I have cancelled it actually. I have to call it again. Alright, which one? You want a mixed dislocation?
so on the note slide, which had written material on it, the slide motion.
You want that? I'm sorry. Okay. Alright, I thought you want to see the motion. I'll come back to that. Yeah, this is the one you were talking about. So that's what we saw. In the case of a screw dislocation, there could be more than one place, but on one plane, if it is traveling, it is traveling like this, right? At times, when the dislocation is moving in a crystal or slipping in a crystal, after all, moving dislocation is a moving strain field because there are strains around the dislocation. Okay. And a strain field can be obstructed by another strain field in the crystal if they are present. This could be dislocation, this could be imperfection, this could be other strains which can come about by the other kind of defects. So it is possible that dislocation is unable to slip further at a point in the crystal, and dislocation wants to move. You are applying stress, you are increasing temperature, you are doing many things to the crystal possibly. So how should it move further? If it is an edge dislocation, the only way it can move is it should change the slip plane, because slip plane is unique. and to change the slip plane it has to jump up or jump down, because slip plane is unique. It has to either jump up or jump down. That motion of a dislocation is called the climb motion of an edge dislocation. Edge dislocation is climbing up or climbing down. Okay, that's a dislocation motion perpendicular to the plane of slip. Okay, therefore it causes the incomplete plane either to shrink in size or it allows it to expand in size. If it's climbing down, a positive edge dislocation is climbing down, mean part plane is expanding. That's what we mean by climb down. Part plane has to expand in size, whether it is a positive edge dislocation or negative. So in other words, you can say climb up and climb down with reference to the positive edge dislocation. It remains the same for negative dislocation also. So when part plane shrinks in size, dislocation is climbing up. Now a part plane expands or a part plane contracts, where the atom is going to go or atom is going to come. If it contracts in size, atoms have to leave the edge of the part plane. And where do they go? They go in the neighboring vacant locations. So ultimately what happens to the volume of the crystal? Increases or decreases? Since these atoms which have left the edge of the part plane have gone and occupied the vacancies have got lost from the crystal. And if there is a vacancy present in the crystal, it occupies as much volume as one atom does. So therefore there will be a decrease in the volume of the crystal. Number of atoms have remained the same, but number of locations where they can sit has reduced. Those vacancies are gone. So when the part plane shrinks in size, there is a decrease in volume. Similarly, when the part plane expands, atoms from the neighborhood have to come and join the edge of the part plane, and thereby they leave behind the vacant locations. So volume expands. So this is not a conservative motion of the dislocation. So we have to either add atoms or we have to the edge of the part plane, or we have to take them away from there. And since I am saying the volume is either increasing or decreasing in this motion, I call it a non-conservative motion. And alternatively, as I already said, vacancies are playing role. The vacancies are either getting created in the crystal or they are getting annihilated from the crystal. Right? So climb up, as I said, part plane shrinks in size. For a positive edge dislocation, it goes like this. For a negative edge dislocation, it goes like this. Okay. Climb down, part plane expands in size. For a positive edge dislocation, it goes like this in the crystal. For a negative edge dislocation, it goes like this in the crystal. Alright. That's the meaning of climb up and climb down. Let me show you with the picture as to what is the meaning of this. Part plane is shrinking in size or part plane is expanding in size. So this is an edge dislocation here. In this edge dislocation, I remove one row of atoms from here. This row of atoms is removed. So I have the part plane only up to here. That row of atoms is gone from there. And the configuration here tries to go up by one step. But these dislocated atoms which are removed, they have to go, let's say this here there was a vacant location. Maybe this atom jumps here, this atom jumps here, and this atom in turn jumps there. So it will come and occupy the vacant location. Vacancy is lost. This is the process of climb up. And opposite of this is going to be climb down. If suppose I start with this dislocation, I add a row of atoms here. If I add a row of atoms, I have to bring some atom from here, neighborhood. It is brought here. Okay. and thereby it becomes a vacant site, and this vacancy in turn can come from here. So this atom from here can jump into there. So vacancies will be somewhere in the crystal neighborhood of the dislocation line, but this part plane is extended like this.
So volume
That's
increases in this case.
naturally volume increases in climb down and volume decreases in climb up. That you can see from this picture itself. And go from here to there, there is a decrease in volume. You go from here to there, there is an increase in volume. From this configuration I come to this configuration, it is climb down. From this configuration I go to that configuration, it is climb up. Alright? That's the climb up and climb down motions of the dislocation line. Now, as I said, in a screw dislocation, there is no unique slip plane. Since there is no unique slip plane, so if there is an obstruction to the motion of a dislocation, it can change the slip plane right at that location and start moving on that location, in that direction. Right? Let me show that. There is a screw dislocation like this in the crystal, which is moving in that direction, the slip plane. Right here it finds an obstruction. It cannot move. So what it can do is, for this dislocation line, as I said, this is also a slip plane. So it can start slipping on this. What would happen is, it has moved up to here. From there it has gone there. But he has formed a step here. Right? Then it will move on this one. It will keep moving. It goes on moving like this till it comes out of the crystal on the surface. So that's the direction of motion has changed. It's gone from this to this. This is what we call the cross slip. Means crosses over to another slip plane. Dislocation line, instead of moving on this slip plane, has begun to move on that slip plane. Right? In the crystal, that's also a slip plane for it. Let's try to write that. So it can move on to another plane, comes across an obstacle, it will glide on 111 provided applied stress on 111. Okay, maybe I think what I want to say here is, its start can probably on one bar plane. If it was moving on, pardon? It was moving on 111 plane, okay, and it comes up across an obstacle, it can start moving on 1 bar 11 plane. 111 and 1 bar 11, you have seen that they intersect each other somewhere. So this can move on this, provided the shear stress is enough on that. That's only your consideration. The shear stress is actually which you had applied on the 111 plane earlier. If its component on 1 bar 11 is sufficient, it shall start this, or you may have to increase the applied shear stress so that it can start slipping on 1 bar 11 plane. So that's the cross slip, or the screw dislocation slips over, or means crosses over to another slip plane. I think this is regard the static and dynamic properties of dislocation. We shall move on to see two-dimensional defects, which are called the surface defects because they are two-dimensional in nature. Though I said that this two-dimensional is not a surface, geometrical surface, it has certain thickness, a certain volume of the crystal is in defect. As I said when I started these imperfections, the external surface of any crystal is an obvious imperfection. Here I show you that this is probably, let us say, an FCC crystal. In the FCC crystal, I have this central atom on the face surface, and these are the corner atoms which are its neighbors. And there are 4 atoms on this surface, the bottom surface and the back surface, which are also its neighbors. Similarly, I have the 4 neighbors here. So these 4 neighbors, the face centers, these 4 neighbors are the face centers, and these are the 4 corners for this central atom here. Alright, that means these are the 12 neighbors in the FCC, and it is bonded to the 12 neighbors. Like this. And these are the 4 neighbors also, it is bonded to. Suppose this is broken away and that becomes the surface. Then what has happened is these 4 neighbors from this atom have been removed, and means I have broken away these bonds 1, 2, 3 and 4. They are the 4 bonds which are broken. But I have not only broken the bond for this, I have also broken the bond for that. I also broken the bond for that. I also broken the bond for this and for that. So any bond is broken for the 2 neighbors. The energy increase now because of this will be shared by both of them. So these atoms and these atoms are now, once it becomes the surface, it's a high energy atom as compared to the atoms inside. They have all the 12 neighbors. But this is the one which has only 4 neighbors on the surface and 4 below. 8 neighbors. It doesn't have these 4 neighbors. So the energy or the enthalpy of this atom goes up. So to show that, here this has only 4 neighbors on the external surface. This is the external surface, and 4 neighbors are inside, 4 are gone. So energy of this neighbor, this atom, is increased by the fact that number of neighbors removed into the bond energy and this is shared by both of them, so it is 2. This is the energy increase of this atom. Same is going to be true about this atom, same is going to be true about this, same is going to be true about this, and same is going to be true. So on the external surface, whatever is the area, total energy is increased for each atom, so that we have to see how much it is increased for all of them. Okay. So for the whole area of the surface, it is increased. it is increased equal to, of course, the factor of 2, you know, number of neighbors, bond energy. If bond energy is expressed per mole, then you have to divide it by 1 mole, because you are talking about one particular bond, right? And then this is to be further multiplied by number of atoms per unit area of the surface. That shall be the increase in the energy or enthalpy. As I told you, this is not getting compensated by the increase in the entropy which goes with it. Therefore, there is a free energy increase which will be slightly less than this. So this is what is happening on the surface, and we have the extra energy. Everywhere you see these point defects, we had increase in enthalpy, enthalpy of formation. Dislocations around this, I had all strains and strain energy increase, enthalpy increase. Then now I have a surface, energies, bonds are removed, so energy of atoms which are on the surface, that is increased. So what are these defects? These are all the defects which are increasing the enthalpy of the crystal, right? They all go to increase the enthalpy. Only it's the point defects which can lower the free energy by increasing the corresponding value of the entropy, but others are not increasing the entropy as much. Well, besides the external surfaces, we do have internal surfaces in crystals. These some of the internal surfaces which we shall describe. One of them is called a grain boundary or the high angle boundary. It's a boundary between two crystals. In other words, if I have a solid which has more than one crystal, means a polycrystalline, maybe millions of crystals, orientation of two neighboring crystals need not be same. It would be different. And as a result, now, as a result, when the atoms are coming at the boundary region, they do not find themselves suitably placed to be part of this crystal or that crystal, because the orientations are different. Let me just show you that with the help of a small picture which I tried. This is one crystal, this is another one, and this is third one, and they are all meeting in this region. Just see this is the boundary here, that's a boundary there, and the boundary is going here. These neighbors which are here, you see this distance between this atom and that atom is shorter than the normal distance. So either I can have this atom or I can have this atom, I cannot have both, right? Similarly here there is enough space, this can be there, that can be there, but when I come here, this and this may find a distance to be shorter. Either this is there or this is there, both of them are not there. In other words, this is a region which is not as thin as I have drawn the line. These atoms in around this region, you will find that either one is there or other is there. So for example, I put this one, I cannot have this atom here, this atom will not be there, it cannot be there. Or it's possible that they compromise both of them and sit somewhere here, they extend the bond length here, they extend the bond length here, and they compromise position they can sit. In other words, what would happen is, in the same space, each atom when it's arranged will be finding itself in a non-crystalline manner. Neither it is a part of this crystalline arrangement nor it's a part of that crystalline arrangement. And also they will not have as many neighbors as they have here. So for example, here in this two-dimensional picture, this atom has 1, 2, 3 and 4 neighbors. It may not have 4. Okay, so that number of neighbors is getting reduced. In other words, out of the 12 in FCC, if I have now 10 or 10.5 on an average, that much energy is gone up. Like we showed it for the external surface, atom's external surface. So this region which is inside the crystal, a two-dimensional defect, is also giving rise to an increase in energy or enthalpy of the crystal. So this is called a grain boundary.
How does these grain boundaries come into the existence inside the crystal? It is crystalline.
Crystalline solid, if it is not a single crystal. Normally when we solidify a melt, we end up getting a polycrystalline solid. We do not get a single crystal. Growing single crystal requires a lot of effort. For this I shall show you how the solidification occurs when I come to there in the course. I will show you that if I need a single crystal, I must have only one nucleus to start with. But when from the melt, when I am solidifying this, from the melt when we are solidifying in general on its own, I get our polycrystalline solid where millions and billions of crystals are present, and they all start growing in different orientations. When they are growing, while growing, there is a space in between. While the liquid is used up, no more liquid is there, they impinge on each other. Once they impinge, different orientation, that's how the grain boundary region comes about. Okay. Alright. So this is a high energy region, but the angle of misorientation is usually exceeding 10 to 15 degrees. And such things are called simply the grain boundaries. Not high angle grain boundaries, simply the grain boundaries. Each one of these crystals, which is let us say FCC solid, it is FCC copper. This is a copper crystal, that's another copper crystal, this is another copper crystal. Each crystallite of a copper is called the grain in the polycrystalline copper. So this grain is a boundary between these grains. Is it clear? This is a surface which is curvilinear. It need not be a straight line or not be a flat plane. Okay. There are others which could be flat planes. But before we talk about that, similar to this grain boundaries, I could have interface boundaries or interface boundary, which would be identical to this. Identical in the sense, this crystal I said FCC copper now, FCC copper, FCC copper. So these are same crystallites, so I call them grains. But suppose this is an FCC copper, this is HCP zinc, okay, and this is another let us say BCC, another phase, could be iron. So these are there, they are there in the present in a solid. Then this crystal is different from that crystal, is different from that crystal. Then I do not call it a grain boundary, I call it an interface boundary. Okay, this is called I shall define the phase in the next class, and we also call it interface boundary. It's an interface between these two phases. Both names mean the same thing, but the character is the same. Like in the grain boundary, the misorientation is very large, and the atoms in between do not find either part of that crystalline arrangement or the part of the other crystalline arrangement. So that's what I talked about, interface or interface boundary. Then we have the low angle boundaries, tilt boundary which has an array of edge dislocations, and a twist boundary which is an array of screw dislocations. I shall show you the tilt boundary where the angle of misorientation is a few degrees, usually 4 or 5 degrees or maybe less. see, this side of the crystal and this side of the crystal is a small tilt, and the angle of misorientation you can see is very small but slightly exaggerated. Actually is given by this angle. This is small angle, and this actually is the same crystal. Maybe you can say that dislocations have come and arranged one over the other. These are all positive edge dislocations which are arranged one over the other because they interact like this. Tension underneath are nullified by the compressions here. Tensions underneath here are nullified by the compressions of this, and tensions of this are nullified by the compressions of this, and so on and so forth. So they are arranged one over the other, but it has caused a slight tilt on the two sides of the crystal. There are more number of planes on this side and less number of planes on the bottom, therefore there is a tilt. That's why it is called a tilt boundary. And this tilt angle, let us say, is theta, and the Burgers vector of the dislocation line is B, and the distance between two dislocation lines is h. Then we define B by h is equal to tan theta. Since theta is small, it is approximately theta in radians, of course. Similarly, the situation when array of screw dislocations arrange themselves on a plane. When they do so, they form a twist boundary, as if one crystal with respect to the second crystal is twisted like this, because that's what is called a twist boundary. And these are the flat planes. Like here, the plane of this is the defect plane, or two-dimensional defect is here. So this is the tilt boundary, is a crystallographic plane, right? It is not a surface like the grain boundary. It's not a curvilinear surface, it's a flat plane. Same is true about the twist boundary. Right. Next we shall have stacking faults. These are also planes, crystallographic planes. It's a fault in stacking. Stacking, let us talk about in a close packed plane, or close packed crystal like FCC. You have seen the stackings are A, B, C, A, B, C, let us say in this stacking goes on, which is perfectly, it's a FCC crystalline solid. One plane misbehaves and this plane is not present, it is missed from its location. What shall be the configuration if that happens? A, B, C, then A is missing. Right? So what has happened? You see locally here, it's an HCP arrangement. Is HCP going to have higher free energy or lower free energy in an FCC crystal? Higher or lower? Higher. If HCP was to stay as a low with lower free energy, the crystal itself would have stayed as HCP. Crystal is the very fact the crystal is staying as FCC, HCP is going to be a higher free energy. So in this small volume in which atoms are, they are high free energy, and this is where the defect is. Same is true in HCP AB-AB stacking. If somewhere a C plane comes in, locally there will be an FCC arrangement, and that shall be a high free energy region. Okay, this is what is a stacking fault. Now I'll show the twin boundary. This always is, you can say it is kind of a spatial stacking fault. Good. That's gone, I think. Is it gone from here? Digital is gone out from here. Where is this? All right. This is spatial stacking fault which always come in parallel, in couple. That's why it's a pair. This is twin boundary. This is another twin boundary. But what happens to crystal? Let us see the arrangement of the crystal on this side is this. On this side, it comes as a mirror reflection. Which again reflects back. So, within the same crystal, it is possible. The crystalline arrangement here is shifted with reference to this, and this boundary, twin boundary, acts as a mirror plane. So this side of the crystal is reflected on the other side, and this you can call it a spatial stacking fault because it always comes in pair. I think this we shall talk about in the next class.